All right. Good afternoon, everyone. Hope you had a good weekend. So what I want to try to do today is see if we can finish off the harmonic oscillator. Before I begin, I did just recently post finally assignment number 2. As you could probably guess, it's just some problems from Griffiths. So if you ever find yourself waiting for the next assignment to come up, what you can do is you can start working on the Griffiths problems, do the starred ones, and those are probably going to show up on the assignment when I get around to releasing it. Okay, so we were going to solve the harmonic oscillator from scratch a second time. And so the first couple, the notes that I have up on the screen are exactly what was written at the end of the last class. So let me just remind ourselves what we were going to do. We wrote down the time-independent Schrodinger equation for the harmonic oscillator. What we had to do is put in the harmonic oscillator potential. We redefined a bunch of these constants in terms of this parameter z. And when we rewrite the time-independent Schrodinger equation in terms of z, we kind of boiled it down to this, where we had to define another collection of constants, and that was k. It's proportional to energy. Okay, so our kind of realization was, well, if we imagine going to very long x is proportional to z. So if x is huge, then z is huge. We're going to imagine we find such a large value that we can ignore this minus k. And then that gives us a simpler differential equation where we could immediately write down a solution. And so it's this exponential type function. But then what we said is, well, if I take a look at this, if I go to large x, this is an approximation for the large x solution. Well, this term with e to the positive z squared over 2 is just going to blow up. There's no chance that we would ever normalize that. So this b coefficient has to be 0. And so we expect at large x, our solutions are going to have something like this involved in them. Now, we know that that's true because we've already solved the harmonic oscillator. Here's the first two states, the ground state and the first excited state. And this exponential factor here is exactly this exponential factor in both these states. And if we were to write this down for the the second excited state, we would keep that factor. So with the next state, the next state, and the next state, they would all have this factor. What changes actually is the x dependence in front of this exponential factor. And if you think about it, the way that we were generating these states in our previous solution is we were acting with the raising operator a hat. What did the raising operator have? It had a d by dx. And so if I differentiate this with respect to x, I get a 2x that comes down. That's where this x came from. If I acted with a plus again, I'm going to first take this derivative with respect to x. I'll get the exponential. But then when I take this derivative, I get a 2x come down. I'm going to get an x squared. So I'll have an x squared term. If I differentiate again, I'll get x linear and x cubed. And then I'll get x squared and x to the 4th, and so on. And you can see what's going to happen is our states are going to alternate between even and odd powers of x in whatever polynomial sits in front of this exponential. And what we're going to do today is we're going to come up with another way of figuring out what that power series is going to be in front of this exponential. And what we're going to find is we're going to get some solutions that are going to involve even powers of x, and some solutions that are going to involve odd powers of x. And so let's watch for that as we go through this solution. Okay, so what we're going to do is the following. The strategy is to return to the full time independent Schrodinger equation and try a solution for our stationary state that is of the form, it's going to have this exponential that we guessed is going to be part of the solution for a large x, but we're going to have some other function of z that multiplies that. And we're going to try to figure out what this other function of z is. Okay, so what we have to do is we have to find derivatives with respect to z. So if we do a first derivative, okay, what are we going to get? We have to do product rule because we have two functions of z here. So the first thing we'll have is a dh dz, and then we have e to the minus z squared over 2. And then we have, let's see, now we're going to get h times the derivative of the exponential. The derivative of the exponential is going to return the exponential. So we'll have h times e to the minus z squared over 2. And then we have to do chain rule and take the derivative of the argument of the exponential. It's going to be minus 2z, but then it's divided by 2. So we pick up a minus z. And so there it is. Okay, so we could write this as dh dz minus z times h e to the minus z squared over 2. All right, that's the first derivative, but our Schrodinger equation requires the second derivative, so we have to do it again, and we have to do more product rule. So the second derivative is going to give us what? Okay, so let's take the derivative of what's in the bracket. We'll get two derivatives of h. And then we have to do product rule here again. So we're going to get minus h and then minus z d by dh. Sorry, dh by dz. And then we have our exponential. Okay, and then we have to take the derivative of the exponential. That's going to bring down a minus z. So it's minus. Then we get the bracket untouched. Then we multiply by z, and then we get the exponential. Okay, so I think that's the derivative. It looks a little messy. We can clean it up slightly. So two derivatives of h. And then let's see, is there anything that we can collect? We get z times dh dz, and we have z times dh dz. They both have minus signs in front of them, so we should get a minus 2 z dh dz. And then what else do we have? We just have a minus h, and then we have a plus z times h. And with a z here, so this becomes a z squared. Okay, so we get the z squared minus 1 all multiplying by h, and then we have the exponential multiplies everything. Okay, so that's our two derivatives of our stationary state that we're looking for. And what we're going to do is we're going to put that into our time independent Schrodinger equation. Let me remind you of what it looked like. So this is what we just worked out. It's a bit of a mess, but then it has to be equal to z squared minus k, where k was that thing that was proportional to energy. Okay. But remember, we're writing our stationary state in terms of some h that we're trying to find times what we think the large x solution must look like. All right, so I'm going to take this stuff, put it on the left-hand side. But let's see if we look at this. z squared times h times the exponential, z squared times h times the exponential, that is the same on both sides. So that's going to cancel. And if you put it in, what you're going to get is 2 derivatives of h minus 2z dh dz. Okay, so that's the first two terms untouched. We're going to cancel this one. We're still going to have the -1, but then we're going to have a k. I'm going to bring it to the other side. So we're going to get a plus k minus 1. So it's plus k minus 1. And both those things multiply h. And that's 0. So this now is effectively our reduction of the time-independent Schrodinger equation. It has two terms. I'm going to label these terms B and A as important terms that will work out. I said two terms. It actually has three terms. We're going to focus on these first two for a second. So this is our effective time-independent Schrodinger equation. All right. Now, the way that these differential equations were solved 300 years ago is that we assume a power series solution for h. If you think about it, I think I've said this last time, when we solved these differential equations earlier in term, we wrote them down as either like a times sine plus b times cos, or a times e to the ijx plus b times e to the minus ijx. But those are also series solutions. We're just writing the power series in terms of these special functions that we're used to using. Okay, so we're going to attempt to express this h, this unknown function, as a power series. So let me tell you what we're going to do before we do it. We're going to write down the power series, and it's exactly what you think it would be. Some coefficient plus another coefficient times 1 power of z plus another coefficient times 2 powers of z, and so on. And so that's just j equals 0 to infinity of aj h. Sorry, not h, it's z to the power j. Then we're going to take this and we're going to sub it into our kind of effective time-independent Schrodinger equation. You can see we're going to have to take some derivatives of this power series. That's going to lead to a recursion relation in these aj coefficients. And we're going to try to work out what must be true from this recursion relation. That's the strategy. Okay, so what we need are these derivatives. If they're not hard to do because we have just a simple power series. So we're going to get, for the first derivative, j equals 0 to infinity. Let's see, this is just going to go to 0. Then we're going to get just a1, and then it's 2a2z, and so on. In general, it's just aj to the z, j times z to the j minus 1. So it's j aj times z to the j minus 1. And that is what we're going to sub in for a up here. Okay. You can see actually what we're going to have to do is we're going to have to multiply it by z first. When we do that, when we multiply by z, this is going to go back to a z to the j. All right, so let's just keep that in mind. We still have to work out the second derivative. And so 2 derivatives of h with respect to z squared. Well, I'm just going to take the first derivative of this thing. It's going to bring down a j minus 1. So I'm going to get a j minus 1 times j aj z to the j minus 2. I forgot my sum. There's still a sum there. This is still a sum over j equals 0 to infinity. Okay, now if I go back to here, I don't have a z or a z squared multiplying. So if I just sub this solution in directly, I'm going to get a z to the j minus 2. I don't like that. So I'm going to make some changes to this before we go forward. The first thing I'm going to do is I'm going to sub in k equals j minus 2. I'm just going to make a substitution. So let's see. So we're going to have a sum. When j equals 0, k is equal to minus 2. Right? Just put in a 0 here. Our lower limit becomes a minus 2. So we're still going to sum all the way up to infinity. Let's see. J minus 1 is a k plus 1. So we're going to get a k plus 1. And a j is k plus 2. And then we get a k plus 2 and z to the k. All right. Now, notice if I was to actually put in k equals minus 2, I would get minus 2 plus 2 is 0. So that's not going to contribute anything. Same thing for k equals minus 1. If I put in minus 1 here, I get a 0 multiplying all this stuff. That term doesn't contribute. So the first term that contributes something non-zero is the k equals 0. So this is equivalent to d2h dz squared is what we're working on. I'm going to go back to my j variable because it's going to help me with my recursion. But I'm just going to throw away the first two terms, and wherever I see a k, I'm just going to put a j. And so we end up with a j plus 1, j plus 2, a j plus 2, zeta to the power j. And so I like that now. I don't have the minus 2 here. I have just powers, z to the j. All right. So this is what we're going to put into B. And so now our effective time independent Schrodinger equation becomes. Okay, let's remind ourselves of what we have to do. We have to take what we just worked out for the second derivative and then subtract off 2z times the first derivative. And we'll worry about the last term in a second. So we'll start with equation 2. So we have the sum of j equals 0 to infinity, j plus 1, j plus 2, aj plus 2, z to the j. And then we had a minus 2 times the first derivative, and we have to multiply by z. So this becomes a z to the j. But it's just minus 2 j, aj, z to the j. Okay, so it's minus 2, sum, j equals 0 to infinity. Should just be j, aj, z to the j. Okay, good. And then we have our last term, k minus 1 times h. Okay, so it's plus k minus 1 times h. But h was our assumed power series. So it's just aj, z to the j. And all of that has to be equal to 0. So this is going to give us our recursion relation. And the reason it works is because we have every term is the same sum and it has the same z to the j factor. So we could write this. Let's factor out the sum. We have sum which j equals 0 to infinity. And let's see. We have a j plus 1, j plus 2, aj plus 2. And then in the second term, we have a minus 2, j, aj. And then in the third term, we have a plus k minus 1. And there's an aj. And all of those multiply z to the power j. and that has to be equal to 0. Okay, so we're almost where we need to be. The only way that we're going to get this thing to sum to 0 is if everything in the brackets is 0. Okay, so for this equality to hold, we require this to be 0. So what we're going to do is we're going to solve for aj plus 2. Notice that these two terms both have the aj. So I could have written this as minus 2j plus k minus 1 all times aj. So if you solve for aj plus 2, what you're going to find is, let's see, we're going to have to take these to the other side. So it's going to be a 2. How did I write it? It's going to be a 2, and then it's going to be a 1 minus k. Okay, so I think it's a 2. The 2 multiplies j. I should keep that. And then we have a plus 1 and a minus k. And then we have to divide by j plus 1 and j plus 2. So j plus 1, j plus 2, and all of that multiplies aj. And this is our recursion relation that for our coefficients in our h that we defined, this power series in z. So this is our recursion formula for the expansion coefficients. The expansion coefficients are just the aj. All right, so let's think about this just quickly before we move on. Notice the recursion relation steps j by 2. So if I put in like an even value of j, like 2, 4, 6, and so on, I'm going to calculate the next even coefficient. So if I put in a 2, I'll calculate the coefficient for 4. If I put in a 6, I'll calculate the coefficient for j equals 8, and so on. On the other hand, if I put in an odd value, I'll only get out odd coefficients. So this is already naturally separating into even and odd powers of z, and so that's going to continue. So let's see what happens. J even. So if I wanted to calculate a 2, I would put in j equals 0. So j equals 0 is my first even value of j. And what is it going to be? It's going to be a 1 minus k over 1 times 2. So it's 1 minus k over 2, 0. Let's continue with the evens. Let's take j equals 2. So that would be giving me the coefficient for a 4. So I'd get 4 plus 1 minus k. So it should be 5 minus k. Divide by what? 3 times 4 is 12. And that's a4 in terms of a2. But I already know a2. So that's equivalent to 5 minus k times 1 minus k divided by 2 times 12, which is 24, and a0. Okay, and this recursion just continues indefinitely. And so I could calculate all of the even coefficients in terms of a0 if I wanted to. So let's do the j odd case. All right, so if I wanted to get a 3, I would pick j equals 1. Okay, and j equals 1. I'm going to get 2 plus 1 is 3, so I'll get a 3 minus k. And then I'm going to get 2 times 3. I'm going to divide by 6, and that's a1. And then I go to j equals 3. That's going to give me a 5. If I put in j equals 3, I'm going to get 7 minus k. divide by 4 times 5 is 20. And that's in terms of A3, but I already know A3, so it's 7 minus k times 3 minus k. What's 6 times 1? 20 is 120 A1. And again, you can just keep going. And so notice what's happened here is we're going to get all of the coefficients except for A0 and A1. Those are still unknown. And why is that? It's because our time-independent Schrodinger equation is still a second-order differential equation. It still has two unknown integration constants that you have to use, say, boundary conditions or normalizations to get. And so the A0 and the A1 are like our integration constants. Okay, so our power series has kind of naturally separated into a series of even powers of z plus a series of odd powers of z. They're still all there, they're just separated into these two series that have the same recursion relation. Okay, so we have two remaining constants, A0 and A1, which in effect are our integration constants. From solving d2 psi d z2 equals and so on. Okay, so to make a little bit more progress, we're going to try to investigate some of the properties of the even series. And so let's see what happens. So let's consider what happens at large J. So actually, this first step doesn't require us to think about even or odd. We're just going to go to this recursion relation. And I'm going to say, well, what if J was really huge? So 2J is going to be a big number. I don't care about the plus 1. And I can always pick J large enough that the minus K I can ignore as well. So in the numerator, I'm just going to get 2J. In the denominator, J plus 1 is going to be J. J plus 2 is going to be J. I get J squared. 2J divided by J squared is 2 over J. Okay, so this is approximately 2J over J squared times a to the J. This is our recursion relation again. All right, so that's just 2 over J AJ. Let's try a few terms for J even. So now I'm going to focus on the even part of our series and see what we can learn. All right, so I'm just going to make up a large value of J. I'm going to happen to choose J equals 100. So what would this tell us? This would be 2 over, actually, I guess I'm choosing J equals 98. J equals 98, which the recursion relation would then give me a 100. So it's going to be 2 over 98 times a 98. 2 over 98, a 98. Okay, but if I put in J plus 2 is 98, then I get 96 here. I'll get 2 over 96, a 96 for a 98. And so I could write this as 2 over 98 times 2 over 96 A96. All right, but for A96, I could write that as 2 over 94, A94. And you can see that this is just going to keep continuing. So this will be probably the last one I write, A94, and this process just keeps going. But 2 over 98 is just 1 over 49. So it's 1 over 49 times 1 over 48 times 1 over 47, A94. But I could just keep going, and I could do 1 over 46, 1 over 45, all the way down until I hit A0. Okay, and so continuing in this fashion, we get AJ is approximately some constant. Maybe the constant is really just A0, but this is J over 2 factorial when J is 98. This is J over 2 factorial when J is equal to 96, and so on. And so this is J over 2 factorial. So my even part of my power series, I could write as some constant, and I'm going to sum only over the even terms of J, and that's 1 over J, 2 factorial, Z to the factorial, Z to the J. So to be honest, I like Griffith's books a lot. Like, they're easy to read. I find they're pretty insightful, but this part of it I found wasn't done very clearly. So I'm giving a little bit of extra detail here. Okay, so what we're going to do now is we're going to make a substitution. Make the substitution K equals J by 2. The reason I'm doing this is because the sum only the even values of J is a little bit awkward mathematically to handle. It's going to get a whole lot more clear if we could make this a sum over all integers. Okay, so that means J is 2K. That's going to be a nice substitution because now I'm going to get J is 2K divided by 2. It's just K factorial. And if I want to sum over even values of J, I should sum over all values of K. Because if I put K equals 1, J is 2. K equals 3, J is 6. Okay, so it's still only the even values of J. All right, good. So H even Z is equal to, C doesn't change. Now our sum is over K, and we have 1 over K factorial, and we get Z to the 2K, like so. And let me just emphasize now, this is now over all integer K, that's even and odd values. Okay, the other thing I'm going to do is I'm going to say Z to the 2K is the same thing as Z squared to the power K. And so what we have then is C times the sum over all K of Z squared to the K over K factorial. All right, good. Now, what does this look like? What is the sum of x to the n over n factorial? Which special function? What's that?
Taylor series?
Yeah, it is the Taylor series for what function? It's the best function in the world.
The exponent.
That's right. It is the exponential. It's exactly the exponential. So this is C, and our x is like the z squared, and so this is e to the z squared. So there's no minus sign, z squared. Okay, so this is going to bring us to the part where we're going to realize we're going to have to do something to fix a problem. So let's recall that what we ended up doing is we said our stationary state, we were going to assume was of the form hz times e to the minus z squared over 2. Let me go way back to the beginning. That's the very first thing. In fact, we made this observation at the end of last class that our high large X solution should be like this. And then what we proposed is this combination to represent our stationary state. And so now what we've done is we've gone and we've worked out, at least for the even powers of Z, what H looks like. Okay, so, and for the even powers, we got this e to the z squared. If I put that in here and multiply by e to the minus z squared over 2, we're going to get something that goes as, so therefore, the even part of our wave function, or our stationary state would go as e to the plus z squared over 2. And that's not good, because it would still mean that for large X, for large Z, this would diverge, and it's not going to be normalizable. We need our wave functions to go to 0 at plus minus infinity for the position X. So if we have H even going as e to the z squared divided by 2, it doesn't matter, then, H even is e to the z squared, then our wave function, or the even part of it, is going to go to e to the plus z squared over 2. This blows up for z or x large, still not normalizable. So we started with a wave function at large X that was not going to be normalizable. And we said, well, let's try to find the H that multiplies our large X solution. It's still not normalizable. And so we're going to have to come to some kind of resolution. So the resolution is that the power series for H even must terminate. If we sum over all values of J even, we get this exponential, which we've just shown is going to present us with a problem. So it must be that we don't sum all terms. We have to truncate that sum somehow. That recursion relation has to stop. And for above a certain value, it must be returning zeros for all the other coefficients. So it must terminate. So in other words, there must be some max value for J. Let's call that n, say J equals n, after which the recursion for aj plus 2 returns zeros. Okay, I'm going to write down the recursion relation again, because it was a little while ago that we had it. It's way back here. So it's 2j plus 1 minus k. So it's 2j plus 1 minus k. And then it was divided by j plus 1, j plus 2, and then we have our AJ here. All right, good. I think that's what we had. Now, we're looking for a way to make this return a 0 for AJ plus 2. The denominator is not going to do it. Like these are just, I'm still thinking about the even values of J. I put in a 2, 4, 6, 8, even a 0. The denominator is not going to help us. So what do I require? I require the numerator to be 0. So to get a n plus 2 equals 0 at, say, j equals n, we require that our numerator 2n plus 1 minus k equals 0. Okay, so that just means that k must be 2n plus 1. All right, so that would terminate our sum. Let's see what happens. So if we select n an even integer, so even integer, we will terminate the recursion for even j, but not odd j. Okay, because look, if I put in an n is even there, then I can, with this value of k, terminate that sum. But if I put in j is 3, and then this is like a 4 or something like that, I'll never get the odd coefficients going to 0. And so we could go through the same sort of argument that we just did for the even series, and we could do it for the odd series, and we'd come to the same conclusion. If we sum all terms in that recursion so that we have an infinite power series, we're going to get a wave function that diverges. So the resolution is, if we terminate the even series with an even value of n, all of the odd coefficients have to vanish. On the other hand, if we decide that we're going to terminate the odd series with an odd value of n, then the even series doesn't terminate. And so we're going to have to say all of the even coefficients are going to be 0. And so we'll have solutions where we have either only even powers of z or x, or only odd powers of z or x. And that's what I was trying to have us have in the back of our head, because we've already solved the harmonic oscillator. And here's the first even, or the first solution, and it's an even one. There's no odd powers of x. The only power of x here is x to the 0, which would be an even one. And then for the next one, it goes odd. If I wrote down side 2, it would have a constant plus x squared. If I wrote down side 3, it would have x plus x cubed, and so on. And so it would alternate between even and odd powers of x. And we're getting the same sort of result here from our recursion relation, where we could have either only even powers of z or only odd powers of z. Okay, so therefore, when we have a terminated even series, the entire odd series has aj equal to 0 for all j odd. Okay, and then we could argue the other way. we could say, let's not focus on the even series, let's focus on the odd series. Now, it turns out that it ends up being a little bit awkward because the math doesn't work out as nice. We don't get like a j over 2 factorial that we could rewrite as a k factorial. So it's more awkward, but it's possible to do. I showed you the way that was a little easier to work through. So we could argue the other way too. If we terminate the odd series at j equals n, where n would have to be some odd number, like 7 or something like that, then we would have to require that aj equals 0 for all j even. So what we get are solutions for this h of z that either have all even powers of z or all odd powers. I shouldn't say all, I should say only even powers or only odd powers of z. In either case, the series, the power series, terminates when j equals n such that k is 2n plus 1. If you think about it, this is how we construct our infinite set of solutions, right? We get an infinite set of stationary states, and the way we generate it is we say, okay, let's first truncate the series for n equals 0, and then we'll truncate it at n equals 1, and then n equals 2 and 3 and 4 and so on. And you do this and you get an infinite set of solutions that go even powers, odd powers, even powers, odd powers, even powers, odd powers, and so on. Okay, watch this. This is pretty fun. However, remember that we defined k. K was just a collection of constants, and it was 2e over h bar omega. So therefore, this n that we're using to truncate our series is equal to 2e h bar omega is equal to 2n plus 1. Let's divide by 2 and multiply by h bar omega. E is going to be, when we divide by 2, we get n plus a half, and then we have to multiply by h bar omega. H bar omega, n plus 1/2. This is exactly the energy of our stationary states that we found when we factored the Schrodinger equation and made these raising and lowering operators. So this is exactly the same as before. Okay, so that's nice. It must mean we're on the right track. So what I'd like to do is I'd like to try to see if we could write down the first few solutions for the wave function or the stationary states. So let's write down the first few solutions for the stationary state psi of n. Okay, I'm going to write down the recursion relation again. So it was 2j plus 1 minus k over j plus 1 times j plus 2, all multiplying aj. But now what we're going to do is we're going to say k is equal to 2n plus 1. So that means 2j plus 1 minus k is 2j plus 1 minus 2n plus 1. Okay, so the ones cancel. And this is the same thing as, let's see, I'm going to write it as minus 2, and then it's n minus j. Okay, so this is the numerator of our recursion relation. And so it becomes aj plus 2, and the numerator is now minus 2, n minus j, j plus 1, j plus 2, aj. And our wave function, or our stationary states, are h of z times e to the minus z squared by 2. Okay, so our goal is to find the power series. So let's try it. So we'll start with n equals 0. Let's try to find the ground state. Okay, so this is an even power, or an even value of n, and so we would say aj is equal to 0 for all j odd right from the outset. And all we have to do is say, okay, what are the surviving terms in the even series? So I'm going to put in j equals 0 to try to calculate the A2 coefficient. So this is j equals 0. It's going to be minus 2. Well, n is 0 and j is 0. And so we just get this simple expression where we have 0 on the numerator and this equals 0. So if A2 is 0, then by default, A4 is going to have to be 0 because A4 is determined from A2. And A6 is determined by A4. They're all going to be 0. And so, therefore, H0 of z is just A0. And we could write down our wave function, our stationary state, psi of 0 is just A0 e to the minus z squared over 2. This is identical to what we had last time. E to the minus m omega 2 h bar x squared. So this is identical if we use our definition for this parameter z. M omega over, what is it, 2h bar x is how we defined it. And we'd have to do normalization to find the value of A0. But that's because, remember, A0 is just like one of our integration constants. And one way to determine the values of integration constants is to use normalization. Okay, so we got our ground state. So that's good. Let's do n equals 1. We're going to do a few of these, and we're going to see what emerges. So we're going to try n equals 1. Okay, so this is an odd value. So we would right away say aj is 0 for all j even. And we're only looking for now odd power solutions. So we'd say, okay, A1 is just another integration constant. I don't know what it is. But if I found it, I could find A3 is minus 2. So we're going to have to do j equals 1. Oh, but n equals 1 and j equals 1. So we get 1 minus 1 in the numerator. So it doesn't really matter what the denominator is, but it's 2 times 3, A1, and that's 0. So then A5 is 0, A7 is 0, A9 is 0, and so on. Okay, so that means H1 of z is just A1 times z to the power of 1. And so that means our stationary state, the first excited state, is H1 times that exponential, but h1 is just a1 z. And this is e to the minus z squared over 2. Again, this is identical to psi1 of x, which we wrote down at the beginning. Let's see, I don't remember what all the normalization constants were, but I got them here. 3/4. Oh, it's not gonna fit. So z, and then it's always the same exponential factor, x squared. All right. Okay, so let's do n equals 2. So this is back to, I think I'm going to do n equals 2 and n equals 3, and then we'll stop. So n equals 2, even. That means aj is 0 for all j odd. And now what we're going to try to do is we're going to try to find a2 using j equals 0. But this time we're not going to get a 0, actually, our first time. So it's -2 n minus j. N is 2, j is 0. Divide by j plus 1 and j plus 2. And multiply by a0. So let's see. This is -4 divided by 2. I hope it's a -2. Yes, -2 a0. All right, so now we have 2 non-zero terms. We could try, let's just see what happens if I try to calculate a4 by using j equals 2. So we're going to get -2, then it's n minus j, but n is 2, and we just picked j is 2. And so it's going to be what? 3 times 4, a2, but this is 0. And then a6 will be 0, a8 will be 0, and so on. And so therefore, our h power series has an a0 term. And then it has -2 times a0 times z squared. And that means our wave function for n equals 2 is a0, 1 minus 2z squared, e to the minus z squared over 2. But remember, this is just proportional to x, so this is like a 1 minus 2x squared. I'm not going to do any more, but if we did n equals 4, we would have a 1, we'd have a z squared, and we'd have a z4. And then for 6, we'd get a z to the 6, and so on. Okay, let's do one more. Let's do n equals 3. Okay, like always, we'll start by saying n is odd. That means aj is 0 for all j odd. And we have to find a3, and we use that j equals 1 and the recursion relation. So it's -2 n minus j, j plus 1, j plus 2, a to the j. And did I do this right? So it's -2 divided by 6. So I get -3rd. Is that right? Let's see. No, didn't do that right. What did I do wrong? 2 times -2. Yeah, I don't know. Something's not right. J plus 1 is 2. Yeah, j equals 1. Ah, yes. Good. Thank you. Good. So this is -4 over 6, so that's -2/3. That's what I wanted. -2a1 over 3. Perfect. Okay, You could probably guess what's going to happen if I try to find the next odd term. This is going to be j equals 3. Let's see if I can do this one right. Minus 2 n minus j, but those are both 3 now. Good. So 4 times 5, 8, 3, but that's just 0. Okay, so that means our H3 is going to be A1, 1 minus 2, sorry, not 1, it's going to be z minus 2/3 of z cubed, I think. And so that means the third stationary state is going to be A1 z minus 2/3 z cubed. So that's our h, and then we just have to multiply by our exponential. There it is. And so here you can see the odd powers of z or x are merging. If we did n equals 5, we'd get a z to the 5th term in there. Okay, so what I want to do is I want to go back and look at these solutions, and let's examine the polynomials that we're getting. In fact, I'll do something silly here. I'm going to move this over, and I'm going to put in a z to the 0 here, which is just 1. Okay. This has a special name. It is called the Hermite polynomial, and this is h0. Okay, and h0 of z, let's say. Then we go to n equals 1. This is h1 of z. And then when we go to n equals 2, this is h2 of z. And here's h3 of z. In fact, I should be careful. These are proportional. They're not exactly the way the polynomials are defined. Let me say they're all proportional. Okay, good. So in general, the nth stationary state is given by, so there are some normalization constants. This is like the A0 constant, but then there's some other factors in here. And we'll talk about some of these in just a second. And then we have our hn of z, and then we have our exponential, like so. These are called the Hermite polynomials. I think, I could be wrong, but I think a lot of people might call this Hermite polynomials. But my understanding is that this is a French name, and so they wouldn't say Hermite. Any case, those are the polynomials. This is the person who worked them out originally. He was interested in a problem in probability. The way that you could understand, I don't know all the details, but this is a Gaussian function, right? You don't need to write this down, but if I was to write down a Gaussian distribution, there would be some prefactor, but then it would go like e to the minus 1/2 of x minus mu over sigma squared. That's a Gaussian function. So this is a Gaussian with mu equal to 0, 0 mean, and sigma equal to 1. Okay, so he was working on some problem in probability that involved some differential equation. He wrote down the same recursion relation that we did, and he figured out all of this terminating the power series and all that stuff. Okay. So, all right, good. So 10 minutes left. So what I'm going to do is I'm going to write down some of these Hermite polynomials. So let's make a table. We'll have n in one column, and then we'll have h of n in another column. All right, so n equals 0. The first Hermite polynomial is just a 1. N equals 1, it's 2z. N equals 2, it's 4z squared minus 2. N equals 3 is 8z cubed minus 12z. N equals 4 is 16z to the 4th minus 48z squared plus 12. This is the last one I'll write down, but it goes on forever. Oh, crap. So it's 32z to the 5th minus 120 z cubed plus, sorry, I said 160 z cubed plus 120 z. All right, so a couple things I want to notice about this. I've already emphasized it, but let's do it again. All of the even values of n result in even powers of z in the polynomial. So this is even powers only. And then if I look at the odd ones, z cubed, z to the 5th, z cubed, z. And so this is odd powers only. Now, these numbers, the coefficients, are not the same coefficients that we wrote down. Let's look at the n equals 2 case. We have a 4 minus 2. But if we look at our n equals 2 solution, we have a 1 minus 2. Well, actually, sorry, it was 4z squared minus 2. We have minus 2z squared plus 1. So what's important is that the ratio of the coefficients are the same. It's a -2 ratio. There's just an overall scaling factor, which we could just absorb into this A0. Again, if I look at the n equals 3 one, 8 and 12. So if I was to divide by 4, this would be 2 and 3. And with the 3 on the lower power. And if I look at our n equals 3 solution, there's the exact 2/3 ratio. Okay, so again, the overall factor doesn't matter. It's the relative coefficient of the different terms that matters. And then we did get that exactly right. The reason that they have, if you look at the first coefficient in the highest power in every one of these polynomials, it's 2 raised to the power n. So 32 is 2 to the 5, 2, 4, 8, 16, 32. And so they've chosen by convention to make the coefficient of the highest power equal to 2 to the n. This is by convention. All right. And so what we've done is we've rediscovered this power series. You'll see others. In this course, when we do the hydrogen atom, we will see, for example, like the Legendre polynomials. And the same sort of thing. It's just solving a slight variation of a differential equation. If and when you take your E&M course 301, maybe some of you have taken it already, you'll see Legendre polynomials there as well. And it's the same sort of thing. It's the solution to some differential equation where we set up a recursion relation to try to figure out the relationship between these coefficients that lead to a power series solution. Okay, good. So I want to show you one other thing. And what I'm going to do is I'm going to share this screen. So let's share the screen. Let's open up a browser. Okay, so you may have noticed that maybe sometime last week, I put a new link up on the website. And so I just want to show you in the last few minutes this link. So Python code to visualize the time evolution of the probability of a quantum harmonic oscillator. what I wanted to do for myself, and what I'm going to show you now, is that I wanted to see that the quantum harmonic oscillator has some of the features you'd expect from a regular harmonic oscillator, a classical oscillator. If I had a mass on a spring and I displaced it and let it go, it would oscillate. It would have two turning points where it momentarily comes to a stop, and it would move fastest through the origin. And so actually what I'll do is I'll show you some notes first. So the notes will describe what I'm trying to do. So here's the Hermite polynomials again. All right. So this is our solution to the wave function, the solution to the full time-dependent Schrodinger equation. Remember, the way we do that is we have some coefficient, and then we have our stationary states. We just worked out the stationary states of the harmonic oscillator. So I'm going to take some superposition of those, and I'm going to put the time dependence back in with our e to the minus I e n t over h bar. That we got, remember, from our separation of variables solution to the time-dependent Schrodinger equation. For the harmonic oscillator, the energy is just n plus a half, okay, times some constants. So what I'm going to do is I'm going to make a particular choice for my Cn coefficients. And okay, so here, let's go back up. So here are our stationary states in terms of the Hermite polynomials. This is the Cn I'm going to choose. Note, remember, Cn squared gives the probability of finding your system in a state with energy En. And so if I was to square this and add them up for all n, those have to add up to 1. If you look at this and think back, if I was to square all of this, this is a real number, so we don't have to worry about complex conjugates or anything. If I was to square my Cn, I'd get e to the minus alpha squared, alpha to the 2n divided by n factorial. That's the Poisson distribution. So I've chosen my coefficients to follow some kind of Poisson distribution. So there's going to be a peak, and then they're going to tail off at the end. So this doesn't matter, but what I'm going to do is I'm going to put all this stuff into our solution for the wave function. This is part of my Cn coefficient. This is part of my Cn coefficient. These are my stationary states. And here is my time dependence that I get from the energy. And what I'm going to do in code is I'm just going to add those up for a bunch of n's. And then I'm going to look at what happens when we let time evolve. Okay, so I'm going to go back here, and here it is. So hopefully this starts up for us. Okay. So this is all on the course website. You can play with it if you like to. Is this going to actually load? Yes. I love it when you finish one time bar and then it just gives you another one. That's my favorite thing in the world. Okay, good. So here it is. So harmonic oscillator. I won't read all the code to you, but I will show you where you can find certain things. Here are the stationary states. Here's the Hermite polynomials. Here are the Cn's written in terms of that Poisson-like distribution. Here is the energy, h bar omega, n plus a half. It's all exactly what I showed you. I'm just going to run this, and it should, after about a minute, make a little animation that we can play that shows the square of the wave function as a function of time. And we're going to be looking for this oscillatory type behavior. That PDF that I showed you with all the notes, it's possible, although slightly involved, I will admit, to take the wave function and analytically show that it produces a Gaussian that has a mean that oscillates with some frequency that's determined by the energy of your system. So just bear with me. This will only take a minute. Is it still running? Okay, yeah, it's still running. We got a little star here. We're waiting for that star to turn into a 1. Yeah. While I'm doing that, can I move this out of the way? Yeah. Good. This was a little faster on my machine than it is on like this online system, but I think it should work. Okay. This doesn't finish in the next, let's say I'll give it another minute. When it finishes, what I want to show you will take only 10 seconds. So, oh, look, it finished. Okay, good. So, what I'm gonna plot here is the absolute square of the wave function. All right, and here it is. This is at time t equals 0. And the reason I chose my coefficient Cn to follow that Poisson type distribution is because it leads to this Gaussian pulse at t equals 0. And so this is at t equals 0 right here. I'm going to press the play button, and it's going to show us how this absolute square of the wave function evolves with time. Remember, the interpretation is that this is a probability density. It's telling you if I made a measurement, what's the probability of finding my particle at a certain value of x? And so it's set up so that right now at t equals 0, there's highest probability of finding it right in the center, x equals 0. And so let's play this thing. And so there it is. It goes fastest through 0. It has 2 turning points, and that's the harmonic oscillation of the probability density for this particular combination or superposition of stationary states. This is called a coherent state because the shape of the wave function squared is not changing as time evolves. It's just shifting in position. And so anyways, that's the harmonic oscillator, recovering the harmonic oscillations that you would expect from a regular sort of mass on a spring type object. Okay, if you want to see the analytic solution that gives you this, those notes are online, but that's optional. All right, thank you very much. We shall see you on Wednesday. No classes tomorrow, just so you know.